Chapter 9: Sound. Now, sound is a form of energy that produces a sensation of hearing in our ears and is produced by vibrating objects or surfaces. The nature of these vibrations determines the type of sound produced. When a string or wire is tightly tied between two pegs fixed on a wooden box like in guitar and then plucked, it vibrates, producing sound. When a larger surface like a drum is struck, it vibrates and produces sound. And when air is blown in a column like in a flute, it causes vibration of air particles in the tube and thus generates sound. Consider the bell we have just seen. This sound is due to the vibration of the bell's gong. If we suspend a tennis ball on a stand with a string and bring it into slight contact with the bell, when the hammer hits the gong, the ball flickers away from the bell and starts swinging. This is because the bell is vibrating, and it is this vibration that causes the sound of the bell. So, let's talk about production and propagation of sound. In order for us to detect sound, it needs to propagate from the source to our ears through a medium. Sound is propagated in form of mechanical waves, which means it requires a material medium to travel. This medium can be solid, liquid, or gas. Suppose you are standing on one side of a brick wall and your friend is on the other side with his ear close to the wall. If you hit the wall with an object, your friend will hear the sound. Here, the medium of propagation is a solid. Again, if you place a bell inside the water container without touching the container and ring the bell, you will be able to hear the sound. The medium of propagation here is liquid. We are also able to detect the sound of a mosquito from a distance because the sound is propagated through air. Let us perform an experiment to show that sound requires a material medium for propagation. We take an electric bell and fix it in an airtight glass jar. The glass jar is connected to a vacuum pump on one end and a power supply with a switch on the other end. On pressing the switch, we hear the bell ringing. Now we suck up all the air in the jar using a vacuum pump. We notice that as air gets depleted in the jar, the sound of the bell gets weaker and weaker. In fact, the sound is not audible at all once all the air is depleted. And this is because the absence of air has created a vacuum inside the jar, meaning there is no medium in the jar now. This confirms that sound needs a material medium to propagate. The vibrating surface causes a disturbance in the medium through which the sound propagates. Consider this tuning fork with two prongs. Vibrating a tuning fork produces a small audible sound. Vibration involves to and fro motion of the prongs about a fixed point called the mean position. The vibrating prongs push and compress the particles near them when moving towards the outer direction, creating a region of high pressure. In this region of high pressure, the density of air is higher than normal. This region is called compression. When the prong moves backwards, it creates a region of low pressure called rarefaction. In this region, the density of air is lower than normal. Thus, As the tuning fork vibrates, the to and from movement of the prongs creates a series of compression and rarefaction in the air between the fork and the listener. This series of compressions and rarefactions constitute a sound wave that travels through the medium. Remember that the medium particles do not move, but rather they pass the disturbance onto their neighboring particles. So sound waves are mechanical waves, and specifically longitudinal waves. And this is because the particles in the medium vibrate in a direction parallel to the direction of wave propagation. A complete sound wave can be considered as a repetition of the pattern of a single wave. That is, it comprises a number of compressions and rarefactions in succession. The length of a single wave is the wavelength. This is the distance between two consecutive compressions or two consecutive rarefactions. Since a compression and a rarefaction follows each other in succession, sound propagation is a periodic phenomenon. The interval between two successive compressions or two successive rarefactions is a constant and is referred to as the time period or simply the period of the wave. The number of waves produced per second is the frequency of the sound wave. We also said that period and frequency are related by the formula frequency is equal to 1 over period. So if the frequency of a wave is 10 Hz, then we get 10 waves in 1 second, meaning that its period is 1/10 of a second. Next, we talk about characteristics of sound. We start with pitch. Now, consider this sound. That one is annoying. Now listen to this one. That's not bad. The difference between these two sounds is something called pitch. It is essentially the interpretation of the frequency of the sound by the brain. Commonly, it's taken as the frequency of the sound. A scream is a high-pitched sound because it has a high frequency. But the cooing of a pigeon is a low-pitched sound because it has a low frequency. The shorter the wavelength, the shorter the frequency, and the higher the pitch of the sound. Simply put, short waves sound high, long waves sound low. Secondly, quality or timbre. Again, listen to this sound. Can you tell how many instruments are playing? Actually, there are two. One is a violin and the other may be a sitar. Sound emitted by any source or instrument has a unique characteristic that distinguishes it from other sounds with the same pitch or loudness. This characteristic is the quality or timbre of the sound. If you listen to the two instruments now playing separately, you can make up the difference in quality of both sounds. Thirdly, tone. Now, have you ever tried to switch on a computer and it makes this sound? It is a disk boot error. If you listen carefully, you will realize that this beep is a uniform sound. It has a single frequency. So the sound wave shows uniformity. This is an example of a tone. A tone is a sound wave of a single frequency. Next, amplitude. Now, listen to these two sounds. Can we go home? Can we go home? What is the difference? This difference is brought about by a difference in amplitude. The loudness of a sound depends on its amplitude. We said that this is the maximum displacement of the vibrating particles from their mean position. A greater amplitude gives a loud sound, while a lower amplitude gives a softer sound. Listen to these two sounds produced by the same drum. The second sound was louder than the first. This is because the amplitude produced the second time was higher. A loud sound can travel a longer distance because it is associated with higher energy. Finally, speed. The speed of sound is lower than that of light, which is why we see the lightning flash way before we hear the thunderstorm. Speed is the ratio of distance to time. For a sound wave, the distance is the wavelength lambda and the time is the period t. So the speed of sound wave is the ratio of its wavelength to period. But because period is equal to 1 over frequency, then speed is equal to frequency times wavelength. Now the speed of sound depends on the properties of the medium through which it propagates. Temperature and density of the medium affects the speed of sound most. For example, if the temperature of a gaseous medium like air increases, its density decreases, resulting in an increase in the speed of sound, and vice versa. Other factors that affect the speed of sound in air are humidity and wind. High humidity results in increased speed of sound. Wind influences the speed of sound depending on their relative directions. Next, audible range. Now, whether or not we hear the sounds produced around us depends on their frequencies. A human ear can only hear sounds that are within a frequency of between 20 and 20,000 Hz. This range of frequency is called the audible range. We cannot hear sounds with lesser or greater frequencies than this audible range. However, different species have different audible ranges. Dogs, for instance, have an audible range much higher than that of humans, and that is why they are kept as watchdogs. They can hear many sounds that are not audible to humans. Sound waves that have a frequency less than 20 Hz are called infrasonic or infrasounds, while those with frequencies above 20,000 Hz are called ultrasonic sound waves or ultrasounds. Next, properties of sound waves. We talk about reflection. Now, when a ball is dropped on a hard surface, it bounces back. Both light and sound behave in a similar manner. A sound wave incident on a hard surface bounces back. This is known as the reflection of sound. According to the laws of reflection of sound, the incident wave and the reflected wave make equal angles with the normal to the reflecting surface at the point of incidence. The incident sound wave, the reflected sound wave, and the normal at the point of incidence all lie in the same plane. Let us demonstrate this using an experiment. We take two identical hollow pipes, PQ and RS, and place them on a table surface near a wall so that their axes intersect at point O on the wall. We then place a clock near the end P of the pipe and a cardboard vertically between the pipes so that the sound of the clock at P cannot be heard directly at the end S of the other pipe. Now we try to hear the sound of the clock at point S. The angle of the pipe RS can be changed by tilting it in a horizontal plane about point O. Here the sound is very feeble. That's a little better. And that is quite clear. This is feeble again. We fixed the pipe RS at an angle where the clarity of the sound is maximum. Now let us measure the angle between the pipe PQ and the normal. This is the incident angle I for the incident sound wave. Then we measure the angle between RS and the normal. This is the angle of reflection of the reflected sound wave. The angle of incidence is equal to the angle of reflection. When the orientation of the pipe RS is changed by tilting it vertically, the audibility of the reflected sound decreases. This is because when tilted vertically, the plane of the reflected sound wave is different from that of the incident sound wave. So only a part of the reflected sound wave passes through RS. This confirms that the incident wave, the reflected wave, and the normal at the point of incidence all lie in the same plane. Next, we talk about echo. Now, it is common experience that when a person shouts in the open air in the mountains, they hear repetitions of the sound coming from the mountains.
Hello! Hello!
Equally, when a person shouts into a well, the same thing happens.
This is an experiment.
These are results of sound waves reflected off the mountains and the water surface. This is commonly called an echo. An echo is therefore a sound reflected from a surface. Consider a big room where a source S, a speaker, and a listener O are in the positions as shown. The listener may hear more than one reflection of sound produced by the source. This is due to multiple reflections produced at different surfaces of the wall. This makes it difficult for the listener to hear what the speaker is saying clearly. The reflected sound is heard until its intensity is lowered to a value where it's no longer audible and finally fades off completely. This phenomenon of persistence of sound in a closed enclosure due to multiple reflections of sound is called reverberation. Reverberation is usually minimized by covering the walls, the floor, and the ceiling with sound-absorbent materials like cardboard, thick curtains, and fiber. The curved ceilings of cinema halls and conference halls are designed to keep the principles of multiple reflections in mind. The curved inner ceiling ensures that sound is reflected to all corners of the hall so that there is even distribution of sound. In some cases, a curved board is placed behind the stage so that the sound waves produced are spread across the hall evenly. In cases where the halls are not designed properly, multiple reflections can lead to uneven distribution of sound. Applications of reflection of sound. First, calculating the speed of sound. Now, consider a person standing a distance d from a cliff. He makes a sound and hears the echo after t seconds. We can calculate the speed of sound. Speed is equal to distance over time. But remember, the sound covered the distance d twice before the man could hear the echo. So speed is equal to 2d over t. For example, a boy standing 200 meters from a wall claps once and hears the echo after 1.2 seconds. Calculate the speed of sound in air. Speed is equal to 2d over t. 2 times 200 over 1.2 gives us 333.33 meters per second. Secondly, sound navigation. The word sonar stands for sound, navigation, and ranging. It is a device that uses sound waves to measure the distance, direction, and speed of underwater objects or depth of the seabed. It consists of a transmitter and a detector fitted at the bottom of the ship. The transmitter produces and transmits ultrasonic waves that travel through water and are reflected back after striking an object or the seabed. The detector catches the reflected waves and converts them into electrical signals which can be interpreted. The distance of the object detected is calculated using the speed of sound in water and the time interval between emission and reception of the sound waves. It is an important technique in determining the depth of the sea or to locate underwater hills, valleys, submarines, icebergs, and sunken ships. For instance, let the depth of the sea be d. The sound waves sent to the seabed have to travel twice the distance from the ship to the seabed. Distance is equal to speed times time. So 2d is equal to speed times time. And so d is equal to speed times time over 2.